Hi everyone. Today I'm going to talk to you about uh, kinetic interplay between photopolymerization and phase separation, and we are going to use some technique called UV transmittance measurement to study this. And this work is done with Dr. Kim and Dr. Sung. Also, the Anna has done some original work. So when we dissolve the polymer in a monomer, they are pretty much dissolved well, just like in polymer dissolving solvent. And then by shining the UV light, these monomers shown in black dots start to polymerize, forming a network. When the network formation is really fast, which can happen at high intensity, polymer did not have a sufficient time to phase separate, so they remain isolated, forming a very small domains, and they are being trapped. And as a consequence, the optical turbidity is not so big, so it remains transparent. But if you do the polymerization at low UV intensity, then slow polymerization happens, and polymers chains have enough time to diffuse, so they form this large aggregate in multiples of microns, and then they can develop significant optical turbidity. This is our postulate. So we did this experiment by changing the UV intensity by dissolving the polyethylene glycol in photocurable polymers. At high intensity, the UV transmittance stay kind of flat, and then eventually it's going up due to the consumption of the photoinitiator. Whereas with low intensity, actually polymer has enough time to diffuse and develop the turbidity. So therefore, actually the transmissions drop due to the physical phase separation, and eventually it's going back up because of the consumption of the photoinitiator there. Okay, so this one shows actually we changed the molecular weight of PEG, and by increasing the molecular weight, the incompatibility increases. So PEG 8000 is most incompatible, and PEG 3400 is the one that's showing some interesting switching behavior. At low intensity, where network formation is slow, polymer have a sufficient time to phase separate, so they show this optical turbidity. Whereas when you increase the UV intensity to higher, now you start to see this decrease in the optical transmissions anymore, and now polymers are entrapped into a small domain that doesn't show any optical turbidity. The smaller PEG, we don't see even the optical turbidity, so we were able to disperse 15% of PEG in this network polymer by photopolymerization. They remain transparent. We also changed the chemical structures, so we tried 3 different polyether series: polyethylene glycol, poly-THF, and the polypropylene glycol. They are all having a similar number average molecular weight, and putting the same amount of polymer, 15 weight percent, in these monomer mixtures. Polypropylene glycol turns out to be the most incompatible. So they like to phase separate out. The incompatibility is so larger, so the turbidity development is much more stronger, and the dip is much more pronounced. So we have shown you that using the UV transmittance apparatus, we can really study the kinetic interplay, that at which intensity there is a switchover behavior from something that can show some optical turbidity to the one that smaller domain that does not show the optical turbidity. This is because the fast polymerization were able to entrap the polymer, not giving enough time to phase separate into a larger domain. And also we find that PPG among PEG and the poly-THF is the most effective one, because it's pronounced incompatibility with a photocurable resin. Okay, thank you for your attention.